we have seen that intervals are connected, intervals in R with usual topology on R are connected, and they are the only connected set in R. And further you have seen that if f is a function from x to y, in fact what is important is on to. F is a continuous function from x on to y, continuous, x connected implies the image fx, but because it is on to it is y, this is also connected. See, what is to be noted is, in case the map is on to, you take any A for A subset of y, f inverse A is subset of the domain, then again if we take f of f inverse of A will be equal to A when f is on to. It is when f is surjective, it is on to. Hence, if you have a separation for y, using that we got a separation for x, and x connected, and in fact we are able to write y equal to A union B imply f inverse of y, that is our x, equal to f inverse A union f inverse of the set B, and because x is connected, already A open, so f inverse of A open, f inverse of B is open. So, at least one of the set, say f inverse of A is empty. So, f inverse of A is empty will imply A is empty. So, if you have a separation for, separation means A and B open sets, non-empty, and y equal to A union B, then at least either A is empty or B is empty, that means the image is connected. Then we have seen that a subspace y of a topological space X is connected mean it cannot, there cannot have a separation in the sense that there exist non-empty sets A comma B, say that y equal to A union B. So, the stronger condition A closer intersection B empty, which is equal to A intersection B closer. If there is a non-empty subset having this property, that means you have proved that y has a separation, that means y is disconnected. Then using this, then we have proved that if we have a collection of connected topological spaces, a collection of connected topological spaces, and the intersection, it has a common point. So, that is the intersection is non-empty, that is intersection of say x alpha here, they are all. So, what we have is, instead of the product we can have x connected A alpha subset of x for each, for alpha belongs to J. So, then and each A alpha is connected, A alpha connected See, that is what A alpha is connected. So, then that imply, and see here we have X a given topological space, X need not be connected, each A alpha is connected and it has a common point, intersection is non-empty, then that imply union is connected. So, union is connected. In general, the union of connected subsets need not be connected, but if they have a common point, so then the union will be connected. Then we have, in a way it is easy to prove that A connected subset of a topological space capital X, and we have a set say capital B subset of X such that A subset of capital B subset of the closure, that means with A if we add sum of the limit points. So, that is we have suppose capital F, that is capital F is subset of limit points, then capital B is our A union F, which is subset of A union set of limit points, that is our closure. So, the set B is between A and A closure, then it is easy to prove that, I mean assume that it has a separation, then using we can prove that the set B is connected. So, A is a connected subset of a topological space imply, if this imply B is connected. In particular when the set B equal to A closure, then A is closure is connected, that is closure of a connected set is connected, then A closure is connected. I mean as these are all relatively simple exercise, I mean one can easily prove that this result, so also one can refer the notes. So, now let us see that how efficiently one can use this notion, that is A is connected imply the closure is connected, to prove that product of connected topological spaces is connected. So, first for this purpose, first geometrically it is intuitively, in fact it is clear that, see for example take x equal to, say we call it x1, say R, or I mean with usual topology on R, that is the topology generated by the collection of all open intervals in R. X1 is in R, we will take x2 also R with the usual topology. Then what is our x1 Cartesian product x2 is nothing but R cross R. This is what we denote by R power 2. So, that is the set of all order pair x1 comma x1 comma x2, such that x1 is in R, here in this case x2 also R. So, x1 is in R, x2 is in R. So, we know already R is connected. Now, let us prove that x1 cross x2 is connected. In fact, this is intuitively clear in the sense that, see, we will use here, this is our, in this case R2 is x1 cross x2, that is our R2. We will write R2 say as a union of, so let us say that fix one element, say here let us call it, this element is say order pair A1 comma A2, this element in R2 is fixed. Then consider a line passing through this order pair A1 A2 and parallel to x axis. This is just any line passing through order pair A1 A2 and parallel to say this, we call it x axis. For us, what do you mean by x axis? Means set of all order pair x1 comma 0 such that x1 is in R. So, that is a subset of R2. Now, take any element in the x axis. So, what is an element in the x axis? We will write it, first coordinate x is in R, second y coordinate is 0. Now, again draw, consider this straight vertical line passing through this order pair x comma 0, passing through order pair x comma 0. Let us call this as, this depends upon the x. If x is some other x, then you will get another line. Suppose we have, this is our y comma 0. So, that correspondingly we call it t suffix x, and this point as, now we call it, if we call this point as order pair y comma 0, then t suffix y. So, now consider this t suffix x, and this line we call it, say this is, let us call it is in the this is vertical lines, this horizontal line let us say h suffix a. A is order pair A1 comma A2. Now, for each x in R, for each x in R, we have, this is our line t which we have denoted by Tx, and t, this h suffix a is this horizontal line, these two line intersect. So, that is for each x in R, the h suffix a intersection t suffix y, in fact at this point. So, this is our, is non-empty, we do not get to say exactly what is this point. So, we can have here any x coordinate is this, and here this y coordinate is A2. So, this is non-empty. Also each HA connected subset of R. In fact, why it is a connected subset of R mean, we can define in a natural way. So, that is what, this is like our R, take an element here, consider this vertical line. So, this what is this point? Here this point is, here the x coordinate is here x, this is x, y coordinate is A2. So, this is an element in H suffix A, and we will say that define f from the real line, that is our x axis, to H suffix A. H suffix A as f of x equal to, see here, or we are considering the usual real line, and H suffix A we are considering this as a subspace of R2 with usual topology. Then image of x is where it intersect HA, that is order pair x comma A2, correct. So, that is x comma A2. See, in other words, what is this H? That is H suffix A is nothing but R cross singleton A2. This is the image of, if you want we can say that this map f is a function from R to R square, R power 2, but range is equal to H suffix A, and it is easy to see that this map. Now, exercise, prove that f is continuous, f is continuous, and the image and f of R equal to H suffix A. So, hence H suffix A, the image of R under this continuous function is connected. So, H suffix A is connected. Similarly, we can prove that this each vertical line is also connected, exactly the same type of. So, we can either define a map from R to here or the y axis, easy to see from the y axis. See here y axis, any element is of the type 0 comma say y, then we can define a map from here. See, just even this is our image 0 comma y. So, you can say that these two parallel line, vertical line, this is vertical line, this y axis. So, they are, one is connected will imply another is connected. Again y, the y axis is connected mean, again we define a map from R to y axis, and the continuous image of R, the x axis equal to y axis, and that is continuous, imply y axis connected. In other words, any vertical line, any line will be connected, even see we can see that any curve. So, all these things are all connected. So, now what is interesting here is we are able to write express, that is R2. Now, see that exactly here R2 is nothing but union. See, this one particular horizontal line we have fixed for each x on the x axis, we are finding a vertical lines. So, then R2 is nothing but union of t suffix such x. This is the vertical line, x varies over R. So, each for, note that what is a each tx is connected subset of R2, each tx is connected, is a connected subset of R2, and we have a common point. So, common not to here. So, here not it is not R2 is, but if you say only the parallel this vertical line, you will get R2 equal to union, but what about intersection should be non-empty. But if we have intersection between even two parallel line, we will not have common point. So, we will not be in a position to use this, that means each is connected, union equal to R2, but intersection is non-empty, we do not have at this stage. So, now instead of T suffix x, you consider a new, now consider say T suffix x prime equal to T suffix x union this particular H suffix a. Now H a. So, this is connected, T suffix x is connected subset of R2, H suffix a connected now and their intersection. So, which is our, if x is here, if x is this point, this is our Tx, this is Ha, they intersect at a point. So, and T suffix x intersection H suffix a non-empty imply the union is T suffix x prime, I mean this I will write in short, connected. So, union of one vertical line and this particular H suffix a is connected. Now, so this is in fact it is subset of R2 is, see why R2, if we take a point, say any arbitrary point, this point will be in the, draw a line passing through that and parallel to y axis. So, this point will be there, that is what it will intersect here, that is some, every point in R2 will be in one of the Tx. Suppose if we call it, this is our x comma 0, this line is our Tx. So, that point, any arbitrary point in the plane will be in one of the line. So, this will be the union, but this is a subset of union of Tx is subset of Tx subset of Tx prime. So, this is subset of Tx prime for each x in R, and further each Tx prime is also subset of R2. So, it is subset of R2, hence what we have is R2 subset of union, and that union is subset of this we have denoted by Tx prime. So, now this Tx prime, each Tx prime is connected. Now, if for x in R, for x in R, T suffix x prime is connected. So, this is connected. So, this is what we have written, T suffix x prime is connected, and we have a common point. See, this is because this one point order pair A1 A2 and this what we have denoted by A, order pair A1 A2 is in the fixed vertical this horizontal line, that in fact what is H suffix A is the line parallel to x axis and passing through order pair A1 A2. order pair A1 A2 is we have fixed in the beginning. So, this belongs to in fact H suffix A, which is subset of T suffix x prime. So, we have a common point in each T x prime, that is T x prime, that is order pair A1 A2 belongs to intersection of T x prime such that x is in R. So, now each T x prime is connected and union is R2, hence R2 is connected. So, exactly, so the same idea, in fact proving that R2 is connected, we will see that we do not require to use this idea, I mean that product of connected space is connected. In fact, later we will introduce what is called pathwise connected, and we can, it is easy to see that these spaces are R2 or Rn, these are all pathwise connected, that is pathwise connected is more general, I mean for any 2 point essentially can be joined by a curve. So, that we will see. So, but now this is not just for the plane, now in place of R2 consider any topological spaces. So, exactly the same idea we will use to prove that the product space is connected. So, that is what this we leave it, it is an exercise. In fact, now prove that x1 x2 connected topological spaces, that means there is a topology tau 1 on x1, another topology tau 2 on x2, these are all connected topological spaces. Then the product space, then x1 cross x2 is connected. See, exactly same way we will fix mean we will assume that x1 cross x2 is empty, mean empty set is connected. So, we will assume that x1 non empty, x2 is non empty, mean the Cartesian product is non empty, and hence we can fix an element say A, which is order pair A1 comma A2 belongs to x1 cross x2. See, geometrically the same way we can denote the same set. See, we have fixed, this is like our order pair A1 comma A2, this is A, this is in x1 cross x2, again the same way. So, we can similar to this we will define what is called here for each x1 belongs to capital X1, fix x1. Now, if we define a map, define say f from x2 to, in a natural way we define from x2 to x1 cross x2 as f of an element in a capital X2 is x2, this is equal to image of x2 is order pair x1 comma x2. So, this x1 is fixed, that means this is in x1 is always singleton x1 cross capital x2, x2 varies. Again the same way this map is continuous, x2 is connected imply this x1 cross x2 is connected. So, that is what essentially you fix a point in the x axis x1 and you vary the elements in the from the y axis. This is x2, then this line is connected. That is similar to saying that this, or we can just say that x1 cross x2 or x1 cross r, this is connected. And similarly you fix a element here and this vertical, this horizontal line, and again use the same idea. So that means you will have this x1 cross x2 is connected, and here you are fixing an element and you are considering a similar to a line passing through order pair A1 comma A2. So, in fact what we will do here is, in fact we will see that the same idea how we are going to extend to on arbitrary. I mean here by induction exactly similar to R connected, imply R cross R is connected, you can prove that x1 cross x2 is connected. So, proof is exactly same. Now, in place of finite collection, let us consider, first I will consider let xn tau n belongs to say set of natural number, that is our index set. Say let us call J is our index set, in this case set of natural number, that is our index set is n. So, what is the idea here is, we wanted to prove by induction x1 connected, x2 connected means x1 cross x2 connected, then assuming that the result is true for n, that means whenever x1 x2 xn connected, then x1 cross x2 comma xn connected. Now, we have a xn plus 1. Now, this one space this is connected, xn plus 1 connected, again we will define a here this one space, this is like new y connected, then xn plus 1 connected, that means this Cartesian product is connected, but we will have to identify this an element here is of the type x1 comma x2 xn with an element in capital X suffix n plus 1, say small x suffix n plus 1, then we define a map from this set to or this space to x1 cross x2 up to x suffix n plus 1. This as, so f of this, see this first element is in x1 cross x2 cross xn, xn plus 1 is in x suffix n plus 1, the image is x1 comma x2 comma xn plus 1, and you can prove that this is a continuous function, it is on to, in fact it is a homeomorphism, that is 1 1 on to, f is continuous, the inverse is continuous. So, hence by induction we know this is connected and xn plus 1 connected, this Cartesian product is connected with product topology. So, but that is same as, I mean here the image, so that will be image is x1 cross x2 xn plus 1, then that space is also connected. So, what is enough to have is, we are going to fix one element. So, first let us fix an element say small a belongs to here. So, in this particular case it is a sequence a n belongs to set of natural number. that is what is A mean, that is f is a function from natural number to union x n, n 1 to infinity, or n varies from natural number such that f at n equal to a n, that belongs to capital X n. This f is what we call it A. So, this is a element in our product space, in this case phi x n, n 1 to infinity. Okay. Now, that is how we have defined. We are fixing one element in the, like fixing an element in the R cross R or x 1 cross x 2. Now, we will consider the set for each element here. So, we are going to define fix, that means x of, we call it a1, a2, a n. It is like this is going to be finite product of the given sets. So, in fact, this is same as set of all order pair. See here x 1 comma x 2 comma x n, n is fixed. N plus 1 onwards, the fixed element a n plus 1, here a n plus 2, a n plus 3 and so on. This comes from our fixed, already we have fixed a 1, a 2, a n, this is known. So, such that here x j belongs to where our capital X j for all j varies from 1 to n. In fact, this is same as we use this notation, that means we have taken the countable index set so that we can easy to understand. So, that is this is same as capital X 1, x small x 1 varies from capital X 1 cross capital X 2 cross capital X n, then cross singleton a n plus 1 cross singleton a n plus 2 cross etc. This is our space. So, this is what our x of a1, x of a1 comma a2 comma a n. This is a subset of phi x n n 1 to infinity, our product space. So, now this is like again we can define a map from x 1 cross x 2 cross x n. So, we can define a map from x 1 cross x 2 cross x n to this space. So, what we have denoted that by, okay, let us call this as say some y. So, y. So, to y as f defined as f of an element here is x 1, x 2, x n. So, image is x 1, x 2, x n, then a n plus 1, a n plus 2 dot dot. So, this belongs to our capital Y, and this map is continuous and the image is Y. So, continuous image of connected set is connected. So, that means each such subspace of the Cartesian product is connected. So, that is what this what like saying that. So, one of the this union of there we have fixed only on order pair a1 comma a2. So, here we have fixed a sequence A equal to A1, A2, AN. Now, this A equal to A1, comma A2, comma A3 dot dot, this belongs to X of A1, comma A2, etc., comma AN for all n. So, this is true for all n in capital N. See, there is here any element is of the type x1 up to xn comes from the corresponding coordinate spaces, after that it is fixed. So, here fixed is an plus 1, then an plus 2. So, they are all already fixed. Here it can be variable. So, in particular A1 belongs to capital X1, A2 belongs to capital X2. So, this element belongs to that set, our what is that is this set belongs to X1 cross X2 cross Xn, afterwards it is like an plus 1, an plus 2. So, instead of singleton just we are writing just a suffix n plus 1, etc. So, this common point each is connected. So, this point union, see this, that is what each x of A1, A2, AN is connected and in intersection of such x of A1, A2, AN. So, this is non-empty, this will imply the union x of A1, comma A2, comma AN is a connected subset of this varies A1, A2, AN varies, or we can say that it n varies. So, this is connected. So, but the question is whether this union equal to our Cartesian product or not. So, we have proved that this union is connected. In fact, here at this stage we are going to use the closure. So, note that what is an element in our product mean phi xn n 1 to infinity. So, it can be any element here is x equal to xn, it is a sequence belongs to phi xn, but so x is in phi xn, each this x of A1, A2, AN subset of our Cartesian product say capital X, each is subset of x, hence the union is subset of x. But here if we take an element in the union mean it will be in one of x of A1, A2, AN. That means after nth stage the n plus 1th stage coefficient should be an plus 1, but on arbitrary element need not be in this collections. So, hence we have that. So, if we take an element in particular A1, A2, AN and we take an xn plus 1 even AN plus 2 where xn plus 1 not equal to AN plus 1, then this will not belongs to yeah, if it is union mean for some after that stage, some stage all the coefficient mean here right now what we are saying this is not in x of A1, A2, AN, because n plus 1 should be here. Similarly, for each element here this union is not equal to the whole space, but still this will be sufficient. So, we call this subspace as, so we have used, let us say, some capital Z equal to this union of such x of a1 a2 an. Now, it is in fact it is easy to prove that let us prove that closure of this space equal to in fact the whole space capital X. So, by x n n1 to infinity. So, for that what is enough to prove is take x equal to x n belongs to the Cartesian product, then prove that take x and prove that this x belongs to closure of Z, that is Z closure. That means what you will have to prove is take a basic open set containing x. That is what enough to prove that for every basic open set containing x, U intersection Z is non-empty. So, start with a basic open set containing the given x, U, a basic open set containing our x. X means x equal to the sequence x n n1 to infinity. So, now this, but because it is a basic open set, then U, in fact this is the same reason we have taken countable collection. That means basic open set means what? X out finitely many, the remaining components are all the whole space. That means a basic open set will be of the type U1 open set in x1 cross U2 and open set in x2 cross say some UK open set in xk. After that it is the whole space xk plus 1 cross xk plus 2 cross etc. See, now it is, this is a open set containing the given point x. So, U open and xn, x belongs to here means what? Xn belongs to Un. So, now in fact, so using this now prove that this basic open set in fact intersection with what is easy to prove that it is in fact. So, what will happen to U intersection x of, so in this case this x of a1 a2 ak. So, x of a1 a2 ak, this set itself non-empty, and this x is subset of the product. This will imply U intersection capital X is no for Z. So, this is subset of Z. Z is union of such x of a1 a2 ak. So, this will imply U intersection Z is non-empty. So, and that will imply our started x belongs to Z closure, that is x belongs to capital X implies x belongs to Z closure. So, that will imply Z closure is subset of the capital X, which is the Cartesian product. So, n1 to infinity, hence Z connected implies Z closure is connected, that implies the capital X is connected. In fact, there is no difference between this proof and instead of taking countable collection, if we take X alpha belongs to an arbitrary J, exactly instead of fixing A, fix some A alpha belongs to J. Then just you can repeat, the idea is same, only the notation here we can see that instead of writing there, we will write phi u alpha, where u some alpha 1 up to u alpha n or u alpha k, they are open in the corresponding x alpha 1 x alpha k, and the remaining u alpha will be the whole space. Yeah. So, thank you.